Welcome to the MCPS Algebra 2E Semester Exam Review video. This is Unit 5 video. We're going to go over pages 18 to 20 in the final exam review packet. It's best if you've already attempted the problems and then go back with me, watch the video, and check and make sure you got the answers, and hopefully I'll explain anything you didn't understand. All right. So, here we go. It says, a person flips a two-sided coin, heads or tails, and rolls a six-sided number cube, numbers 1, 2, 3, 4, 5, 6. How many different outcomes are there? So there's a couple different ways you can think about this. One strategy I use is go like this. Heads, tails. 1, 2, 3, 4, 5, 6. So they're just asking us how many outcomes are there. They're not asking us for a sample space. But maybe we'll review sample space also, just in case. So here, how many outcomes? Well, we could have heads with 1, heads with 2, heads with 3, heads with 4, heads with 5, heads with 6. So that's 6 different options. And then I could also have tails with 1, tails with 2, tails with 3, tails 4, tails 5, tails 6. So that's 6 more options. So in total, there's 12 options. And there's something called the basic counting principle. Here we have 2 options, here we have 6, multiply 2 times 6, and you get 12 total outcomes. If we were going to do, so how many different outcomes are there? 12. Okay, I'm going to add one more question in there. What if I asked you for the sample space? So sample space, we're going to put a French bracket. We're going to have heads with 1, heads with 2, heads with 3, heads 4, heads 5, oops, heads 6, tails with 1, tails with 2, tails with 3. Now, the order I'm putting them in is not the only order. Some people choose to go heads 1, tails 1, heads 2, tails 2. It doesn't matter the order as long as you've listed all of them, and that's if they're asking you for the sample space. All right. But all this question asks for is how many different outcomes are there? The answer is 12 different outcomes. All right. In the Venn diagrams below, the events shown are A, a person who likes to run, and B, a person who likes to bike. In each situation below, shade in the appropriate area. So, let me see how big my highlighter is. I'm going to make it a little smaller. Okay. In each situation, shade the appropriate. People who like to ride and like to bike. Keyword here, and. They like to ride, so they're in this circle, and they like to bike. They're also in this circle. So in order to be in both circles at the same time, we have to be in this section right here. Likes to ride and likes to bike. So here, people who like to bike or like to, people who like to ride or like to bike. So if you like to ride, you're in this circle. If you like to bike, you're in that circle. So, okay. So it's either this or that, as long as you're in this or you're in that. It's okay to be in the and section. These people that are in here, they like to ride, or they like to bike, or they like to do both, and that's okay. Or is very flexible and is more strict. All right, I'm gonna move this up so we can see it better. People who do not like to ride, people who do not like to ride. So let's see. These are people who like to ride inside the circle. So I want anything that's not in that circle. So basically everything that's not riders. All of these people are not people who like to ride. Did that make sense? People who do not like to ride, right? So anyone in here likes to ride. Everybody who's not in there doesn't like to ride. Okay, people who like to ride, so I'm thinking inside the circle, but do not like to bike. So I have to be outside of this, but inside of this. Okay, so I have to stay outside of the biking. You don't like biking, but you like to ride. So that would be a good shading area for that one. All right, wonderful. Two-way tables. All right, so we have 100 people, There's our total. 100 people, male and female, were asked which of the two sports they preferred, hockey or basketball. The results are shown in the two-way table. So we have hockey total, basketball total, male total, and female total. And then these are more specific. Males that like hockey, males that like basketball, females that like hockey, females that like basketball. All right, so one person is selected at random from this group. Determine the following. What is the probability that a person likes basketball? All right. The probability that a person likes basketball. So I'm going to go to basketball. One of the number one mistakes is students go and they take the first number because they know they're in the right spot. They're like, woohoo, 56. But that is not the total. That's the males who like basketball. So make sure, if it's just saying, what's the probability that a person likes basketball? Period. Total basketball people. Lovers are 80 out of 100. So 80 out of 100 would be an acceptable answer. You could simplify that and say 8. Write it as a decimal. The county also says that you can write it as a percent. In my preference is to write it as a decimal between 0 and 1 for probability. So we're going to go ahead and do that. But if you wrote any of those, the county says it's okay. All right, the probability the person is female. Okay, so look, oh, let me erase this each time. Okay, the probability that you're female, go all the way, don't just stop at that 6, female all the way to the end, 30 out of 100. All right, so that would be a decimal of 0.3. Great. The probability that a person prefers hockey and is male. This is a key word here, hockey and male. That really narrows down the field. So we have hockey and male. So we're looking at this cell, hockey and male. Out of all the people, there are 14 that like hockey and male. So 14 out of 100, which would be a decimal of 0.14. All right. What is the probability that a person prefers basketball and is female? So again, we have an and. So we need to find basketball and female. Looks like right here. So basketball and female out of total would be 24 out of 100, which is 0.24. Great. What is the probability that a person is female or prefers hockey? All right, so we've got some ors here. Ors are exciting. We need to think a little bit more about this. All right, so there is actually a formula. I'm going to look over here. Are these probability? Yep, okay. So here we have a formula for the probability of A or B. It says find all the probability of A happening, add it to the probability of B happening, and then subtract the probability of A and B. And the reason for that is there's an overlap. Here's the probability of A happening. Okay, here is the probability of B happening. If you notice, there's a section in there that is overlapping the blue and the green, so I have to take away one of the overlap. So we have to subtract out the A and the B, because then you double count that section. And you'll see how we don't want to double count in the table. So I'm going to highlight. This says probability the person is female, so this, or prefers hockey, or that. Okay, so the probability that they're female is 30 out of 100. The probability that they're a hockey lover is 20 out of 100. And the part that's repeated is this 6. So I want to subtract out 6 so that I don't double count it. And we end up with 44 out of 100, which would be 0.44. All right. The probability, next one, is another or. The probability that a person is male or prefers basketball. So let's think of it another way. Okay, prefers basketball or is male. So I need to include all of these numbers, this one, and this one. So this is another way to think about it. I can add up these two, and oh, but that's 70, and I need 24 more. 70, 80, 94. So it looks like 94 out of 100, or 0.94, would be the probability. All right, now we have some givens. And again, there's a formula over here. If we needed to use our formulas, we could say probability of A given B is probability of A and B over probability of B. So this is one method, is using that formula. So let's see what we got here. Okay, given that the person selected is male, so given that they're male, so the formula said we needed to take the probability of H and M divided by the probability of M. So our denominator is going to be the whole probability of just being male. Probability of male is 70 out of 100. So 70 out of 100 is 0.7. So I'm just going to leave that as that. And then, what's the probability that the person prefers hockey? So of the males, and I'm ignoring all of this. I am given that they're male. I know they're male. I'm ignoring everything else. Out of a total of 70, what's the probability they like hockey? Well, 14. So so the probability of H and M is 0.14. Sorry, I kind of switched strategies there. So if we're following the formula, we have a probability divided by a probability, which ends up with 0.2. If we just say, okay, what part out of this total, 14 out of 70, would also get you 0.2. Okay, so final answer, 0.2. All right, last one. Given that the person selected, let me erase this. Given that the person selected prefers basketball, the probability that the person is female. So given that they prefer basketball, we are ignoring everything else. I can ignore the totals, I can ignore the hockey, given that they like basketball. So my total now is 80. Out of 80, what's the probability that they're female? Well, there are 24 out of 80 that are female. All right, so 24 out of 80, if I simplify that, I get 3/10 or 0.3. All right, the last thing they're asking us to do is determine if these two events are independent. So our person is a male and person prefers hockey, independent events. Use what you know about conditional probabilities to justify your answer. So this right here is a key word. If you miss that, you might show that they're independent, but show it with the wrong formula. Okay, so there is a formula over here that requires independence. And it says that if two events, A and B, are independent, then P of A and B is equal to P of A times P of B. But nowhere in there is there a conditional statement. So this right here is a conditional statement. It's A given B. So we need to use a conditional statement to prove it. And how that works is the probability that a person is male, we need to check and see if that's equal to the probability that a person is male given they like hockey. They prefer hockey. All right, if these two are equal, then they're independent. If they're not equal, then they're not independent. All right, so a person is male. So let's check these two probabilities and see what we got. What's the probability that a person is male? Erase all my scribbles. Probability that they're male is 0.7. Kind of already figured that out. Okay. And the probability that they're male, given they like hockey. Did we do that here? Male given hockey? Nope. Okay. Given hockey, we're going to divide by that total hockey. So given that they like hockey, out of 20, what's the probability they're male? 14 out of 20. So let's check this, 14 out of 20, and see what that becomes. 14 out of 20 simplifies to 7/10 or 0.7. All right, are these two equal? Yes, they are. So because they are equal, this is our conditional, right here, this is our conditional probability. Because they are equal, okay, Are they independent events? Yes, they are independent events. Because the probability of being male was equal to the probability of being male given, if you like hockey, were equal, because they were equal. All right, and I feel like this work over here is enough to justify. All right, wonderful. Great. Now we're going to look at a Venn diagram. Okay. The Venn diagram below shows the percentages of people who eat fruit and vegetables at least once a day. All right, here we have fruit people, here we have vegetable people, here we have people that don't like fruits or vegetables, or don't eat fruits and vegetables. Okay, a person is selected at random. Determine the following. The probability that a person eats fruit. What's the probability of F? Well, if I look here, now, okay, I am going to write the answers in, well, I don't know. Okay. So the answer key on Montgomery County's exam review packet shows percents here, and I understand that here there's percents, but my class practiced writing probabilities as decimals, unless it asked for a percent, in which case we gave a percent. So I'm going to write it as a decimal, but I'll do 1 as a percent so you can see how it would be. But I'm going to go with writing it as a decimal. So the probability that a person eats fruit, the probability of eating fruit would be all of this circle. So 42 and 8, which would be 50. So 0.5 would be the probability. If you're writing percents, you would say 50%. Okay. The probability that the person does not eat vegetables. Okay, everything outside. So these are people that do eat vegetables. I want everything outside of that circle. So I need to add up these guys right here. 40, 50, 60. It looks like 60.6 or 60%. All right, the probability that the person eats fruits and vegetables. Fruits and vegetables would be this section right here, 0.08. All right. The probability the person eats fruits or vegetables. Fruits or vegetables. Could be any of these. So we're going to add up all 3 of those, and we end up with 82.82. All right. The probability, erase that. The probability, given that the person eats fruits. This is important. Given that the person eats fruits. So I am only focusing on this circle. This is the only part that exists to me anymore. I'm ignoring anything else. Given that the person eats fruits, what is the probability that they also eat vegetables? So this, right, is our vegetable area. So what's the probability out of all these people that they eat vegetables as well? So we're going to say 8 over 42. 8% over 42%. Which gives you 16% or 0.16 would be the probability. All right, the probability given that the person eats vegetables also eats fruits. Okay, given that the person eats vegetables, so I feel like we're doing the other circle. Given that they eat vegetables, let's make sure I'm reading this right. Given that the person eats vegetables, that they also eat fruit, that they also are in here. So we have now 8 out of that total, 30, 40. 8 out of 40. Oh, goodness. I just realized I made a mistake here. I'm glad you probably already found it, huh? Okay, so I ended up with the correct answer for the wrong reason. Okay, so up here, when we did this, let's do this again. Given that the person eats fruit, the whole total here shouldn't have been 42. It should have been 50. Good job if you found that. All right. So out of 50%, out of that whole, all the fruit eaters, there were 8% that ate vegetables. Sorry about that. Okay, and that ends up being 0.16. Okay, so down here, we're going to say of all the veggie eaters, which would be 40%, out of all of them, what part are fruit eaters? 8%. So 8 divided by 40, and we get 0.2. All right, wonderful. The last one, this one's a little tricky, so we need to read it carefully, make sure we understand what's going on. Okay. The probability that the person does not eat vegetables also does not eat fruit. Person that does not eat vegetables, so outside of the vegetable, also does not eat fruit, so also outside the fruit. Well, okay, so outside anywhere, it looks like just that right there, 0.18. All right, wonderful. I think we have 2 more problems, and that's the end of Unit 5. So, the probability that Jay gets to work overtime on any given day is 40%. What is the probability that Jay will have to work overtime on 3 consecutive days? So day 1, day 2, day 3. The probability he'll work overtime is 0.4. The probability on the second day is again 0.4. And the probability on the third day is again 0.4. And we are kind of assuming that these are independent events. That if he works overtime one day, it's not going to affect whether he gets to work overtime the next day. So if they're independent, we can use this this A and B independent formula, and the probability of this and that happening would be just multiplying the probabilities. So here we're going to just multiply these probabilities together, and we end up with 0.064. So the probability that he works all 3 days consecutively would be 0.064, or 6.4%. All right, Polly is interested in the upcoming 2 games played by her team. She decides that her team has a 0.7 probability of winning Game 1 and a 0.6 probability of winning Game 2. Assuming that the results of the games are independent, what is the probability of her team winning both games? Same concept, right? So the probability of the first game times the probability of the second game, and you'll get the probability that they win both games would be 0.42. All right, wonderful, and that is the end of Unit 5. Thank you for watching. You guys are preparing well for the final exam. Good job.